Okay, in this video, we continue discussing how to determine a sample size, but we do it from a different perspective. We look at it as a result of understanding an effect size. There's a lot of research out there that will find things that are statistically significant, but maybe not practically significant. So a lot of the research is focusing on, well, you want to, when you produce something, I need to know how significant is the effect. So it's not just a statistical significance, is the change that you are doing research on and your findings, how large is the effect change? And that's we're going to look at determining how much sample, how large our sample should be to get to be able to identify a certain effect size. So effect size, read about it. You can certainly go to Wikipedia. That's a pretty good one. The homework that you're going to do is some questions based on a book by Patton that I put some questions, a short reading with some questions that let you spend more time looking at effect size. From a sample size standpoint, what we're looking at is that when you're trying to, if you've got research and you've got a benchmark, an existing measure, think of a regression R-squared that's already been published. Let's say you've done research, you have a regression model, and you have an R-squared at 0.6. Made that up. And you need to go out and determine, and you want to achieve an R-squared that's higher than that. Let's say 0.8, 0.9, something really high. Well, if your new methodology and your new data is there, it doesn't take much data to identify large changes. If you're going to, if your data shows a large change, you don't need a lot of data to prove that. But if you're looking for small changes, then you're going to need a lot of data to prove a statistically significant difference between a certain value and then a small change. The examples I have here is that if you are polling a presidential's approval rating, and let's say that the approval rating has jumped up from 50% to 80%. And it happened because of some significant event, but let's say that the approval rating. You don't have to ask a lot of people, hey, what do you think of the president? If there is a significant change that's that large, you don't need a lot of data to prove that. But think about it the other way. What if you want to be able to statistically see a difference between a 50% approval rating and a 52% approval rating? That's a fairly small change. Well, you're going to have to ask a lot of people, because that's a small change, and you're going to need a lot of evidence to be able to see a statistically significant difference between those two. So that's how you can think of effect size's effect on sample size. Now, again, read about the effect size, but this particular software, if you go to this website, and you can probably show it in English or if you wanted to, but this software is a free download from this university, and it's called G-Power. And what it does is it does a power analysis. And for what it means for you, though, is that we can use this to identify how much data to collect to achieve a certain power. How much data to achieve to collect to guarantee a certain power. If you're doing research proposal, it's going to take effort to collect data, and you want to be able to collect enough data to have a certain power of your research, of your findings. I'll discuss power in a different video, but it's 1 minus the beta error. So if you go download this, and you can download it either for a Mac or a Windows, it doesn't make any difference, but once you download it, it looks like this. it up. This is what the software looks like. It's a free software, and I'm going to set it up so I don't see the plot. It makes it a little smaller. This is what I'm looking at. So think about the regression problem that we did in class, the 1976 NFL data, when we had 8 independent variables trying to predict the number of wins in 1976 NFL season. And I think the achieved effects are the achieved row that we were trying to get. Well, let me go. I'm going to do a test. I'm going to go into regression. And when you're doing regression, just use the random model. That's the easiest one. And let's say our existing, based on that data that we have right now, our existing, I think we achieved an R squared of about 0.7. And let's say that I want to do research with the goal of identifying it's only worth something to me if I can get an R squared of 0.9. If I can't get if I can't get 0.9, it's not worth doing the effort. So we need a model that's that good. So I'm going to collect more data to get there. The inputs that we have to put in is your alpha error, that's a type 1 error, and your power. Your power is 1 minus your beta error. Typically for the research proposals that I've done, usually you have to have a power of at least 0.85. And these control how much data you're going to collect. Now we have 8 variables in our regression model, 8 predictors. So if I need to go from a 0.7 to 0.9, and let's assume I have really a data that does that shows that significant of a change, this is how much additional data that I need to collect. Only 27 data points. That's not very many. Because if you truly do have data that shows a difference between 0.7 and a 0.9 R squared, it doesn't take a lot of data to identify, hey, there's a significant change. But let's say that we're only trying to be able to say there's a statistical difference between 0.7 and 0.72. We only are looking for an R squared increase of a 0.02. That's a very small change, so the consequence of that is that you're going to have to collect an incredible amount of data to see. So tiny changes require a lot of data. Large changes don't require too much. Keep in mind, I'm not saying that when you collect this amount of data, you're going to see an R squared go from 0.7 to 0.9. I'm saying that if there is evidence of that, you don't need a lot of data to prove statistically that, yes, this model is statistically different than 0.7 and it's now a 0.9. If you want to be able to conclude that, if that really existed, you don't need a lot of data to prove that. You don't need a lot of data to conclude a large change. Small changes, it takes a lot of data. If my alpha error needs to be smaller, it even gets more. Same thing with my beta error. If my power needs to be higher, it's even more. So the smaller your alpha, the larger your power. If you need to achieve a high power, if I need to build a model that achieves a 90% power, you're going to have to collect a lot of data versus 0.85 and 85% power. Okay, that's how we can use this. And later on, as we move through a traditional hypothesis testing, you can see that we can use this to help us identify sample sizes for all kinds of different tests. T-test, ANOVA test, there's all kinds of different ways. And the purpose of this is to identify how much data to collect as a function of something called an effect size. Thanks.